We now turn to arrays. So far, we've only dealt with variables with single values, but it turns out that actually the standard element or the fundamental form of a variable in MATLAB is always an array, which means that a single variable can contain multiple elements. For instance, if we investigate our current variables over here, which are defined in the workspace, and for instance, if I hover over C, I see that it is actually a 1 by 1 double, where double means that it's a double precision floating point number that will be discussed in the lecture, but it's a 1 by 1 variable. And we can also look at this by invoking the size of C, and we see that the outcome is that C is actually a matrix, let's say, with one row and one column. And this is the case for actually all variables in MATLAB. They are all standardly interpreted as arrays with a corresponding amount of rows and columns. So a variable with a single value, that is in mathematics referred to as a scalar. A variable where either the rows or the columns has more than one element, that is what we call a vector. And there are two types of vectors: row vectors, which have one row and multiple columns, so they consist of a row, therefore they are called row vectors, and column vectors, which consist of a single column. How to construct these in MATLAB? Well, let's construct a row vector. Let's call it row vector, and for that we use square brackets. So for instance, we want a row vector with 3 elements, so we just enter the 3 elements and they are delimited by spaces. So for instance, we want the elements 2, 6, and 9 in our row vector. And we see that, well, we can actually investigate this row vector variable by double clicking on it, which opens yet another panel. We see this is a vector, a row vector with 3 elements, 2, 6, and 9. Let's close this. For a column vector, this is similar, but we use slightly different syntax. So let's call this col vector. So again, we use square brackets, but we have to delimit the entries by semicolons instead of spaces. So if we now click on this col vector, we see that we have here a column vector with entries 2, 6, and 9. So those are vectors. Now let's say that we want to access a certain element of a row or a column vector. Let's say we want to access not the first, not the last, but the second element in the row vector. How do we do this? For this we use round brackets. So in order to access the second element in a row vector, we simply use round brackets and then add the index of the number of the element that we want to address. So the outcome for this will be 6, because 6 is the second element in the row vector. Note that indexing starts from 1 in MATLAB and not from 0 like in some other languages. And a similar thing holds for the column vector, where for instance we can access the third element, which would be 9. An interesting technique for accessing the last element is not by simply counting the amount of elements, but MATLAB has a nice trick for that. We can use the keyword end. So if we were to access col vector at index end, this would also give 9, as 9 is the last element of the column vector, col vector. So that leaves us with vectors. Now let's look into matrices. Now matrices have both rows and columns. Now in order to construct matrices, we just simply combine the syntax that we've already learned for row vectors and column vectors. So for instance, let's make a matrix with 2 rows and 3 columns. Let's call this matrix A. We use square brackets as we've done for the other examples as well. And on the first row, we want to have the elements 1, 2, and 3. We then move down a row by using this semicolon operator, and on the second row we want to have elements 4, 5, and 6. And what comes out is this 2 by 3 matrix A, so 2 rows and 3 columns with the elements just the way we entered them over here. In order to access elements of a matrix, of the matrix A, we also simply use round brackets. For instance, if we want to address the element at row 2 and column 3, which would in this case be row 2 and column 3, so the outcome should be 6. And that is indeed the case. So that is how we also construct matrices and access elements of matrices. A nice interesting fact is if we want to, for instance, not select a single element in the matrix, but instead take an entire row or an entire column of a matrix, we can use the colon operator. So for instance, let's say we want to address the first column of the matrix A. Well, we then denote this as follows. So this says all rows, first column, and the output should be the first column of the matrix A, which is 1, 4. So let's do that over here, and that's indeed what we see. Let's just repeat the output such that we see A again. And similar thing if we want to select a row of the matrix, for instance the second row here, well then we just denote this as follows. We take the second row and we take all columns, and the output will be 4, 5, 6. Okay, so that teaches us how we can construct row vectors, column vectors, and matrices. But if we have larger and larger vectors or matrices with more and more elements, then constructing these all by hand will become very cumbersome. Therefore, fortunately, MATLAB has a lot of array creation tools that can be used to avoid having to enter all these things manually. So the first one, which is something we've already discussed slightly before, this is this colon operator. And it can be used to generate a sequence of numbers from a starting point to an ending point. For instance, let's call this, let's clear all variables for now and clean the window such that we have a nice and clean interface. Let's say that we want to make a row vector with elements starting from 1 to 10. Well, we could do this in the following way. So let's call this row vector 1. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So this is still feasible, but obviously if we want to do this from 1 to 100, this will take us quite a lot of time to enter all these entries manually. Now instead we can use the colon operator here as well. So the colon operator, let me call this row vector 2, such that we have both variables in the workspace and we can compare them. So we just have a starting point, we use the colon operator, and then we add an ending point. So from 1 to 10. And we see that indeed the output here has also created a list of numbers starting from 1 with an increment of 1 going to 10. Another nice thing that we can do with this colon operator is we can use increments not only of a step of 1, but also have increments of a step of 2, for instance. So So let me call this again row vector 3 or row vector step 2. And the way to do this is, well, this would be standard notation for a step of 1, but we can add in the middle, then using another colon, we can add the increment or the step that has to be taken in between consecutive elements of this array. And then here we see indeed that this has a list of numbers from 1 to 10. We see that 10 is missing here actually, and we see that the increment is 2 here, so 1 plus 2 is 3, plus 2 is 5, plus 2 is 7, plus 2 is 9. 10 is not included because 9 plus 2 would be 11, and that is outside of the range that we specified here. So that is kind of the way that this colon operator works. Other useful ways for generating these kind of sequences is, for instance, the linspace function. So let's take a look at the documentation of the linspace function. This will create a linearly spaced vector between point x1 and point x2, and this will generate n points in between those two numerical values. So if we, let's say, make a list of numbers between -1 and 1, and we want 1000 numbers between -1 and 1, we can use this linspace function and do it as follows. And we see that the answer is now a row vector with 1000 entries, and if we inspect it, we see that it has a small increment, and the increment is chosen such that there are exactly 1000 elements in this vector. Other useful functions for generating quite common vectors and matrices are, for instance, the zeros function. So zeros can be used if we want to create a matrix containing only zeros. So for example, let's say that we want a matrix with 10 rows and 3 columns containing only zeros. Let's call this matrix B. And we see that the output is a 10 by 3 array, 10 rows, 3 columns, and if we inspect it, this will have only zeros as entries. Similar command is the once function, which by the name already suggests that this will have a very similar output, except there are no zeros, but they are ones. There are lots of other functions here as well that can be used. One interesting function is the I function, which will generate an identity matrix. Again, you can look at the documentation for more details, but let's just generate the 3 by 3 identity matrix D, and we see that this is indeed the 3 by 3 identity matrix that comes out.